This is Geometry Lesson 2.2, Conditional Statements. And the big idea says, conditional statements, those which can be put in the form if, then, are the basis of logical thinking in mathematics. So as we dig into Chapter 2, we're going to deal less and less with physical shapes that we're looking at and doing things with. We will get more into that later in geometry, and we're going to talk about logic a lot here in this section. And today we're going to start by talking about if-then statements. They will relate specifically to geometric figures at times, but not always. As we try and understand exactly what's going on, we'll use other types of examples that may not specifically deal with shapes or even mathematical ideas at all. All right, so conditional statements, if-then statements, are the main idea of what we are covering here in section 2.2. So let's start with some vocabulary words that we need to make sure we understand. A statement, just a regular old statement, is a sentence that's either true or it's false, but it cannot be both. So it's not a gray area. It's either yes, that's true, or no, that's false. For instance, my dog has fleas. That's either true, he has fleas, or it's false, he does not. Okay, there cannot be a true but also false situation. So that is considered a statement. A compound statement, compound means more than one. Okay, it's a sentence that combines two or more statements. So let's take this one. My dog has fleas. And, so now we create a compound statement by adding and. They make him itch. Again, a statement that is true. They either make him itch or they don't. So that's a good statement. When you put them together, that's now a compound statement. My dog has fleas and they make him itch. Now, to jump into the main part of what we're looking at here, a conditional statement. This is a compound statement, so something that has two or more statements. Most of the time we're looking at just two. That can be written in if-then form. So we're going to start our sentence with if, and then we're going to go to then as the result. So if my dog has fleas, then he will itch. So we use the word if and then to combine our statements, and that creates what's called a conditional statement. Here's another one. If the light is red, then you must stop. So it's an if-then statement. That's your conditional statement. Now these are made up of two pieces, the first statement and the second statement, and they have these fancy words that we need to know, the antecedent and the consequent. So the antecedent is the statement that follows if. That would be, my dog has fleas. It follows the if, and the consequent is the then. He will itch. So the antecedent, that's the consequent. The antecedent here is the light is red. And the consequent is you must stop. Notice I didn't actually include the if and the then in that. It's the statement that follows it. It doesn't include the if. It's just the light is red. And the consequent is you must stop. Now it's not always going to be in this order if it's not given to you as a conditional statement. So here's just a compound statement. You must stop when the light is red. So you might, if I asked you to circle the antecedent and underline the consequent in this, you might just go right to the beginning and start circling. Okay, but if you have to rewrite this as an if-then statement, at least in your head, before you can pick which one is which. It's not necessarily the first one, because this is just this conditional statement rewritten. This doesn't say if you must stop, then the light is red. Now, you could word it that way, but the reason I'm showing it to you like this, relating it directly back to this one, is the light is red can still be the antecedent, and the consequent can still be you must stop. So I just don't want you to fall into the trap of always saying the first couple words I see has to be the antecedent and then the next ones have to be the consequent. It's all a matter of the if and the then. If the light is red, you must stop. Now, if you had rewritten it as if you must stop, then the light is red, then now you've changed the antecedent and the consequent, and you could do that. All right, but the order is not necessarily what determines the antecedent and the consequent. It's the if and the then. Okay, so we're going to talk about instances and counterexamples. So an instance of a conditional is when both things are true. Here's one. If you live in, I was going to say Whitehall, I don't know why. Let's say Montague. Then you live in Michigan. So for all of you that are here that actually live in Montague, you also live in Michigan. So this would be considered an instance of a conditional because it's true. If you live in Montague, then you live in Michigan. Now, a consequence is when the antecedent's true, but the consequent is not true. And so one way to think about it is if you live in Montague, well, do you think there's another town of Montague somewhere in the country or somewhere in the world? Yes. So there can be someone who lives in Montague, but it's a different Montague, and they don't live in Michigan. And that would be a counterexample of this conditional. I didn't look that up. The one from the book looked like this. If you live in Springfield, then you live in Illinois. That's the statement that was given. If you live in Springfield, then you live in Illinois. Just like we said, if you live in Montague, you live in Michigan. So this can be true. There is a Springfield, Illinois. But the counterexample, you could live in Springfield, but there's a Springfield in Massachusetts. So the first part, the antecedent, is true. You live in Springfield. But then the consequent, you live in Illinois, that is not true. You live in Massachusetts. Okay, so it is possible for some statements to have instances that are true and counterexamples that are not true. Now, for a conditional to be considered true, or just overall true, it's a true conditional. Every single instance must be true. There cannot be a counterexample. If we're going to say that a conditional statement is true, there cannot be counterexamples. Okay, and then when we're working with these, we're going to start abbreviating them to make them a little bit easier to work with. Let's refocus this for you. And you're going to see it a lot with different letters, but lots of P's and Q's. And this is red, if P, then Q. So P and Q are kind of like variables, and they're going to represent a statement. And then this is a conditional statement, an if-then statement. So P is the statement a figure is a triangle. Q is the statement a figure is a polygon. I can write this as an if-then statement. If P, then Q. So P represents figure is a triangle. So if a figure is a triangle, then, so if P, this is your then. If a figure is a triangle, then And we can always play with the wording a little bit to make it make sense. That figure is a polygon. So this notation, this abbreviation, can represent a longer statement, and then it's just a nicer way of writing it, just abbreviating it. So if P, then Q can represent something. And we're also going to look at Venn diagrams. All right, Venn diagrams, you see this in all different subjects. But what ends up happening is you've got some kind of subject, and then you have kind of like these little folders that are, or subsets that are on the inside. And sometimes they overlap, which means there's some things that are match part of it, but some things that don't. So things that cannot drive cars. How about people? Some people can, right? 16 and up. And these people in here can't, like a newborn child. So we can have these circles that overlap, and some of it is part of this category and some of it is not. You can see here squirrels are completely inside because there are no squirrels that can drive. So all squirrels fit inside this things that cannot drive cars. Now from this Venn diagram, we need to be able to write a conditional statement, an if-then statement. And so you would say, if you are a squirrel, then you cannot drive. Now, if you were looking at this statement, because not all of these fit inside, we couldn't write that statement. If you were a person, you cannot drive. That could be true, that could be false. But since all of squirrels is inside of that, we can actually write this true conditional statement. So this one, you got your subset here, represents your pet. And all of your pets, based on this Venn diagram, are dogs. If you had dogs and cats, it would have to overlap. Some inside are dogs, some outside are not. But this one can be written as a true conditional statement because all of your pets are dogs. So we don't know how many pets there are, but if an animal is, we'll just use the words that they have, my pet, you could say your pet, then it is a dog. All right, so writing conditional statements from a Venn diagram, you're going to see some of that. All right, if you flip it over, let's try a couple examples here. All right, so first, antecedent and consequent. If 2 points are distinct, then there is exactly one line that contains the 2 points. So there's something that we were working with in the last section. And we're going to go ahead and break down this if-then statement. Circle the antecedent, that's the if part. 2 points are distinct. And the consequent, there is exactly one line that contains the 2 points. Number 2, is this conditional statement true? Remember, for it to be true, every instance has to be true. If it's not true, give a counterexample. So if you are a student, then you are taking a geometry course. So for you, you are an instance of this. You are an instance that makes this true. You're a student and you're taking geometry. But just because it's true for you doesn't mean that this is a true statement. So I would say, no, this is not true. I will say a student taking algebra is a counter example. So if you say that a conditional statement is not true, that's not saying that it's always false. There can be instances where it's true. But if we're going to say that this conditional statement is true, there cannot be a counterexample. It needs to be true all the time. So in this case, no, this is not true all the time. Counterexample is a student taking algebra. All right, number 3, rewrite this statement as a conditional. So here's your statement. Dogs chase cats. Rewrite that as an if-then statement. If you are a dog, then you chase cats. You just make it an if-then statement if they're asking you to write it as a conditional. And number 4, give an instance and a counterexample of the following statement. So something that is true and one that is false. So here's the statement. If the area of a rectangle is 30, then the perimeter of the rectangle is 22. Let's start with an instance. So an instance is a situation that shows that this is true, where it works. So remember, area is length times width or base times height. If I'm getting 30, my sides could be 6 and 5. Area is 6 times 5, which equals 30. And if this is a rectangle, opposite sides are equal. Perimeter, you add up all your sides. So 6 plus 6 plus 5 plus 5. So this is 10, this is 12. Put together, that is 22. So this is an instance of this conditional statement. If the area is 30, this is, then the perimeter is 22, this is. But that's not always true. So come up with a counterexample. So we're going to make a shape where the area multiplies to 30. So we need two numbers that multiply to 30. But then when you add up all the sides, you don't get 22. So two numbers that multiply to 30 would be 15 and 2. 2 times 15 is 30. So my area is 30, but perimeter, 15 plus 15 plus 2 plus 2, that's 30, and that's 4. And so this is a counterexample. The area of the rectangle is 30, that's true, but the perimeter of the rectangle is not 22, it's 34. So there is your instance where it's true and your counterexample where it is false.